Greetings. My name is Kathy, and I'm with the Friends of Arlington's David M. Brown Planetarium. And I am here with Dr. Sethanne Howard, and we are going to be talking with you today about black holes. And we are doing this as a virtual online talk, obviously. The planetarium right now is closed because of a construction project, and we hope that it will open in 2022. But until then, we're going to be running some more virtual talks, and possibly as things get better, hopefully with the COVID thing, more and more in-person events as well throughout the year, until we can get the planetarium open and start having our events in the planetarium again. But we're really pleased that you're joining us and watching today. Without any further ado, I'm going to let Dr. Sethanne Howard introduce herself and start her talk about black holes.
Yeah, black holes, and we're going to talk about how they can dance. In case you didn't know, but a lot of people are interested in black holes, especially kids. The questions they ask in school are, what is a black hole, and are we going to live through it? So I will address that kind of question just for the kids, because they're very interested in it. I'm a retired astronomer, retired from the U.S. Naval Observatory. I was chief of the Nautical Almanac Office, which produces the Astronomical Almanac. And it isn't used as much as it used to be because people now do remote observing from telescopes. They don't sit at the telescope with their book very carefully trying to figure out where everything is. But we're going to do black holes can dance. And let's start the talk. There we go. Black holes can dance. I'm Sethanne Howard, Dr. Howard, which is how I answer the phone in case you're curious. It really shuts up the people who are spamming. They think I'm a physician. Works wonders. Okay, there are two things wrong with this picture. Number one is astronomers do not wear white coats. Number two, this is how a lot of people think we discover black holes. And of course, it's not how we discover black holes at all, and we don't wear white coats. So, going on, dark stars were mentioned in the 18th century, actually, as stars that might eat their own light. And Mitchell and Laplace were two scientists who wrote about a star so massive that it would eat its own light. And the largest bodies in the universe may thus be invisible, Laplace mentioned. And that's fascinating. That was predicted long before we got to Einstein, okay? Now we're going to talk about the very basics of black holes. We need Einstein, I'm sorry. Math, there is a little math, but there are places where we don't worry. But if we visit a black hole, we're going to worry. I'm sorry about that too. How do we measure a black hole? How do we make a black hole? How do we see a black hole? And then how we're going to dance. And I'll do the dancing right at the very end. It's adorable video. Okay? Yeah. Now, black holes are not holes. That's one thing to remember. They're not a hole in space, and they're not black. Black holes are not really black. They're invisible, but they're a whole lot of mass in a teeny tiny actual zero volume, which sounds impossible, and it is according to regular physics. So it is impossible according to regular physics, but black holes do exist. So we found them. So something's awry with regular physics. Okay, the basics. Nothing can travel faster than the speed of light. We have to assume that at the beginning. The speed of light is a constant. That's the speed of light in meters per second, almost 3 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 meters per second. Yes. Now, the pieces of a black hole. First of all, there's a singularity in the very center of the black hole. That's inside the black part. It's inside the black hole, and then the outside is blue, and then the edge of the black hole is in dotted white lines, and that's also called the event horizon. So there are three pieces: an edge, an inside, and an outside. And then in the very center, there's a singularity. Okay? Now, let's see what happens. If you're traveling at the speed of light, you are at the edge. If you want to escape the black hole and you're traveling at the speed of light, you won't escape. And inside the black hole, you have to be traveling faster than the speed of light, which nobody can do. So you can't escape once you're inside. And outside is the rest of the universe. And if you're traveling less than the speed of light, you might be able to escape. Okay. Now, inside, there's something, I'm just going to mention this in passing. There's something called the waterfall effect. And it just means the space is falling faster than light, or space is falling faster than time, actually. Space and time reverse. And it's called the waterfall effect because if you stare at the waterfall and assume it's stationary, then it'll look like the rocks are moving up. And that's the waterfall effect. It's an optical illusion. So inside the black hole, waterfall effect. Now, what does light do with black holes? Basics part 2. Light travels in straight lines. Isaac Newton told us that. But is that true? Because Einstein came along in the 20th century and showed that matter can influence light. Light will bend. It won't travel in a straight line. It will bend around a massive object. And I have a couple of examples of this. In Newton, straight line, no change in that wonderful graphic. Einstein, you see a little tiny wiggle in the graphic, and the red line, which is the light ray, bends around the massive object. That's the 20th century. And here's another way of saying it. Light rays bend around a massive object. The more massive the object, the more the light is bent. And black holes are very, very massive. So light will curve around a black hole. Okay? The warp geometry, if you're far enough away, you won't see any effect. As you get closer, you might bend a little bit. As you get really close, you could bend a lot. If you actually head into the black hole, you're going to circle around inside and not get out. Now, what does a black hole? I said they're invisible, but if you look at a black hole, there's an eyeball on the lower right, the little icon showing your eye. And if you look at the black hole and you look at the stars around the black hole, the stars are the little dots with the yellow lines coming down from them. The stars go around the black hole, the little dots of white. No, too far. Can you show the dots so they know what I'm talking about? With the
sorry, Sethanne, our technology is not cooperating at the moment.
Okay. Well, each dot, each starlight sends out a ray of light. It bends around the black hole and comes to your eyeball. And each star in the circle around the black hole will do that. Some will come directly in, bending a little bit, and some will circle the black hole again and again and again and again, and then hit your eye. And so if you look at a black hole, you'll get the next slide, which shows you a black hole, which is strictly invisible and not black, but it's surrounded by a circle of the universe, all the stars around it, circling around and around and around and around, bending around the black hole, coming to your eyeball. That essentially is gravitational lensing, but we won't go into that here. Then that's the basics. So what's outside the black hole? What does space look like outside? Newton says nothing. It's going to be rectangular. Einstein says the black hole will warp space. And one way we show this is this way. It's a way I like that shows the warped space with the black hole in the middle. And it's highly deformed near the black hole. But there are other ways to illustrate this. And this graphic shows 4 ways to illustrate a black hole. You can even do it in 3 dimensions as a balloon to illustrate a black hole. And underneath the balloon is a little black hole with a little companion going around it, the little dip. So that's just ways to illustrate a black hole, none of which are very realistic, because a black hole is a 4-dimensional object. A rule, we've got to have this rule. Black holes require the general theory of relativity. I'm sorry. Einstein gave us the general theory of relativity, and the general theory of relativity gave us black holes. But Einstein, just so you can say you've seen it, I want to show you the equation for general relativity. And here comes the equation. That's it. I'm very sorry. You can say you've seen it. It's going to go away in a minute. But in English, that equation is matter, which is the right side of the equation, tells space-time how to curve. Space-time is the left side of the equation. And space-time, the left side of the equation, tells matter, the right side of the equation, how to move. That's how you say all that math in English. Okay, now we're going to do a little math here. This is obviously a picture of the general theory of relativity, and it's just as simple as it can get. It's a mess, in other words. The general theory of relativity is hard. There's no way around it. So I want you all who are terrified of tensor calculus, which is what it is, take a nap. Because we're going to move on to a little bit of math. Now, obviously, people who are terrified go to therapists to say, I'm in this class and calculus is the easy part. And tensor calculus is even harder than calculus. And tensor calculus is used in the general theory of relativity. So at the singularity, that dot in the middle of the black hole is where the radius equals 0. The radius is equal to 0 at the center of the circle. 1 over 0 is not 0, it's not infinity, it's undefined. And that means that the math, the physics, the astronomy no longer work at the singularity at r equals 0, at the center of the black hole. That's undefined. It's not infinity, it's undefined. The laws break down. And a Schwarzschild black hole, Karl Schwarzschild in 1916 during World War I solved those messy equations to produce the geometry of space-time for a non-rotating spherical mass of mass m. Now, he was in World War I. He was in the German army sent to the Russian front. He wrote his paper, sent it off to Einstein, and was injured in the war and died. So we lost a great scientist due to World War I. But his paper made it to Einstein in time, and it showed Schwarzschild's black hole solution for a non-rotating, in other words, it's not spinning around, spherical mass m. And there's the black hole with the event horizon on the edge, the singularity in the middle, and the Schwarzschild radius is called the edge, same thing. Event horizon, edge, Schwarzschild radius are all the same things. And the radius is the center from the singularity to the edge. That's the Schwarzschild radius. And it's a very useful thing to use because, next slide, we have this is just another way of showing the radius out from the center, or from the side view, it's the red line in the graphic on the side view, and inside the light just goes to the black hole, and at the edge, at the horizon, we wake up because we're going to move on to away from the math. And there they go. I promised you the equations would go away. There's one equation maybe left, but most of the math is going to go away, leaving behind a singularity of, go back one, leaving behind a singularity at r equals 0, which is a black hole. So in this case, if you didn't get the math, trust me. Okay. Now we can go on. The Schwarzschild radius actually is useful because if you want to know the value of the radius, it's 3 times the mass of the black hole in kilometers with respect to the mass of the sun. So in solar masses, if you know the mass of the black hole, you multiply it times 3 and you've got the Schwarzschild radius. It's very simple. And I think I have an example of many of them here. The Earth has a Schwarzschild radius of 9 millimeters. The sun has a Schwarzschild radius of 3 kilometers. And then a 3 solar mass star, which is a star with 3 times the mass of the sun, it's 3 times 3 or 9 kilometers. A 3,000 solar mass black hole is 3 times 3 or 9,000 kilometers. And that gives you an example of the Schwarzschild radii, and the human being is so tiny you can't even measure it. It's tinier than an atom. It's tinier than an electron. Our Schwarzschild radius is so tiny we don't count. But if you could take all the mass of the Earth and compress it to be the size of a marble, in other words, within the Schwarzschild radius, diameter of 18 millimeters, it would become a black hole. So anything can become a black hole if you can squeeze it tightly enough so that all its mass will fall within the Schwarzschild radius. That's not easy to do. So what would happen if the sun became a black hole? At this point, the cat is giving me her opinion, and she's coming up here to help. What would happen if the sun became a black hole? Well, I would ask you this question and ask for answers, but because we're not live, we're live but don't have a real audience, I'm going to answer it for you. Would we notice? The answer is yes and no. Go back. The answer is yes and no, because it's yes, it depends on the value of we. If we is the human race, we would notice because the sunlight disappears and we would die. The Earth, on the other hand, would continue to orbit just as before. It wouldn't zoom into the black hole. It would just orbit in its regular orbit around the sun black hole. So yes and no is the correct answer. The Earth doesn't care, but the humans would all die. Okay. Now, it's important to know that black holes don't zoom around space, sucking up matter. They sit quietly where they are. You can put the first, they don't zoom around space. They sit quietly where they are. And as long as you're far enough away from them, you're far enough away from the Schwarzschild radius, you don't have any worries because it's not going to come and get you. It's going to just sit there quietly until you are stupid enough to come close. And if you get close, then eerie things begin to happen. And if you get to the Schwarzschild radius, you worry. Basically, you worry. Okay. So let's go visit a 3 solar mass black hole. Its Schwarzschild radius is 9 kilometers. So here we go. We're going to go visit this. I'll give you the answer first. The answer is that once you cross the event horizon, you're not going to survive and you're not going to get out. So you're not going to survive the trip, and that's the answer. But why is that the answer? We're going to take a spacecraft, and the spacecraft has 2 astronauts in it, a smart one and a dumb one. The dumb astronaut says, I want to visit the black hole, leaves the spaceship and drops feet first towards the black hole. The smart astronaut stays inside the spaceship, knowing better. Okay, what happens to that dumb astronaut? The closer the dumb astronaut gets, the stronger the tidal pull on the dumb astronaut's body. It's the gradient of the gravitational field in math. The stronger the tidal pull, it's all tides, similar to the lunar tides on Earth. And the closer the dumb astronaut gets, the stronger the tidal pull on the dumb astronaut. And the dumb astronaut is falling feet first. So as the dumb astronaut falls, the feet get stretched out and the head is left behind a little bit. So the body stretches out. And the dumb astronaut becomes longer and thinner, and eventually becomes so long that the bones break apart. Unless you're made of rubber, unless you're a Rubbermaid dumb astronaut, but the bones break, the bones themselves break, the atoms break, everything breaks apart, and you become a long string of spaghetti. And it's all tides. And here is the amount of G forces, the amount of gravity you're going to feel. If you're, let me see if I can read it, 6,400 kilometers away, you only feel half a G, you're fine. But when you get to 10 kilometers away, remember the Schwarzschild radius is 9 kilometers, you feel 150 billion G's. You are so stretched that you're just broken apart in pieces. And we're very clever. Astronomers call this spaghettification. You turn into long, dumb astronaut spaghetti strings. You actually spiral in, but what I'm showing you is if you're really dropping in, but you actually spiral in. Now, what happens is that your toes will enter the Schwarzschild radius first. And as you cross the black hole radius, it'd be like squeezing a tube of toothpaste. The black hole will squeeze you out. And by the time your head gets there, you're going to disappear with a puff of energy. That's called the tube of toothpaste effect. Now, let's drop some things into a black hole just for fun. We have a pink elephant, the Cheshire cat, a toothbrush, and a VW bug. We're going to drop them into the black hole. Do we know afterwards that they are inside? That's a question. Can we tell what's inside the black hole if we saw them drop in? And the answer is no. All information is lost at the event horizon, and this is called cosmic censorship. In other words, there are no naked singularities. The singularity is at the middle. And however, the answer was no. However, Stephen Hawking made a bet with John Preskill and Kip Thorne that there can be, Kip Thorne said that naked singularities are wrong and should be prohibited. John Preskill and Kip Thorne said, yes, they can't, that they can be allowed a naked singularity. And they made it, the guys made a bet, 100 pounds sterling to 50 pounds sterling. And the winner would provide clothing to cover the nakedness of the loser. Now, Hawking conceded on a technicality in February of 1997. He finally said, yes, there can be naked singularities. He wasn't sure, but he just said, okay, I'll cave. Okay. So we can't visit it. What can we do? We can't do much. But if you can't do anything, you make a rule. That's what people do. It's like Congress. So cosmic censorship leads to the rule, black holes have no hair. That's what it's called. What it means is you can't measure anything about a black hole except mass, spin, and charge. Is it spinning around? How much mass it has? And does it have an electric charge? And most black holes are neutral. Some spin, but they all have mass. And that's called black holes have no hair. There's nothing you can grab onto to a black hole to tell you about it. Except, of course, there's always an exception. Stephen Hawking in 1974, this is before the naked singularity bet, Stephen Hawking said a black hole can radiate. This is called Hawking radiation. And it can lose energy very, very, very slowly. It would take a one solar mass black hole longer than the lifetime of the universe to slowly evaporate. And it's not much energy given off. You've never seen it. It'd be it's 1 billion trillion trillionth as bright as a 100-watt light bulb. So that's called Hawking radiation. But Hawking radiation might violate the black holes have no hair. Because if black holes have no hair, how can you see radiation from them? And Kip Thorne and Stephen Hawking challenged John Preskill, is information carried away or not? Kip Thorne and Stephen Hawking said no, information is not carried away. Preskill said yes. And this led to, obviously, another bet. And this bet led to the Black Hole War, which was his battle with Stephen Hawking to make the world safe for quantum mechanics, which led to, can information be carried away? And the answer is a very firm maybe. Hawking radiation may exist and information may not be lost. We don't know, because we need quantum fluctuations of the black hole in order to allow Hawking radiation to carry away information. And we do not have a viable theory of quantum mechanics and general relativity. Quantum mechanics is the physics of the very, very tiny. Black hole physics, general relativity, is the physics of the very, very large. So we don't know is the answer. So, but in 2004, Hawking conceded the bet, but Thorne did not. So Hawking, in conceding the bet, gave a baseball to Preskill that was covered with the entire Encyclopedia Britannica, saying everything in the world can come out of the black hole. And we're not finished yet, because they had more bets. Stephen Hawking bet Don Page, and he lost the bet with Don over whether information that falls into a black hole is lost forever. Page insisted that this would violate the conservation of energy principle. Hawking eventually conceded and paid up the bet. That's the bet they're holding up together, and it was a Marilyn Monroe dollar. He paid him off with a Marilyn Monroe dollar. However, we're not done yet. Hawking changed his mind in 2014. In other words, you see that this has been a real game that they're playing. He changed his mind and said, maybe There's no event horizon at all. There's no Schwarzschild radius. It's incompatible with quantum mechanics. So the real answer requires marrying quantum mechanics and general relativity, and we don't have that, so we wait until we do. We wait, and we wait, and we wait. So while we wait, we have a whole bunch of ideas and not many proofs. So let's see how they're made. Small ones, which are stellar-sized black holes, and large ones, which are supermassive black holes. The small ones, it depends upon how massive you are when you are born as a star. A star like our sun, which is the top image, will evolve during its lifetime until it becomes a white dwarf at the end. That's what our sun will do in another 5 billion years or so. But if you're very massive when you're born, you live hard and fast. And the low mass stars like our sun, the top one, lives slowly a long time. If you're very massive, you evolve quickly, and eventually at the end, you either blow up, leave behind a neutron star, which we won't discuss, or you implode. And if you implode, all the mass goes into the black hole at the singularity, and it forms a black hole. So if you're massive enough, you become a black hole. That's how you make a stellar-sized black hole. Supermassive black holes are formed by black holes that accrete things that go by it close enough to be swept in, or it collides with something, or it merges with something. And they are hundreds to billions of solar masses in size. And they're usually found one in the center of each galaxy. There's one in the center of the Milky Way. There's one in the center of most of the galaxies we see around the universe, a supermassive black hole. How many are there in the Milky Way? The Milky Way has about 100 billion stars, and one of every 1,000 stars that form will be massive enough to end up as a black hole. So if there are 100 billion stars, that means there are 100 million stellar mass black holes. That's a lot for our Milky Way. And there are perhaps 100 billion galaxies visible from Earth. And if each one has about 100 million stellar mass black holes, there are a really large number that I can't count high enough to get to for the number of black holes in the universe. But there are about 100 million in the Milky Way, which is our home galaxy. Now, currently, if you're curious, there are two close black holes. One is a candidate black hole. It's called the unicorn, and it may not be a black hole. We're not sure because it's so light. It's a 3 solar mass black hole, and that's really too light to be a black hole. But it's under study. They're trying to figure out, is it a black hole or not? It's a binary system, 2 stars together, with a red giant star, a red star, and a 3 solar mass black hole. That could be the closest. It's 1,500 light years away. But the one that's for sure been verified as the closest is 1,120 light years away, and it's a triple star system with at least a 5 solar mass black hole. It's large enough to be a black hole. The 3 solar mass is kind of iffy. The heaviest black hole around that we know of is in a quasar, which is very, very distant. It's 3.5 gigalight years away. OJ287. It's been studied by the astronomers in Finland for over 20 years. They followed this and deduced that it's a pair of binary black holes with a mass of almost 2 times 10 to the 10th solar masses, or 2 billion solar masses. That's pretty massive. That's the heaviest black hole we know of. Okay, now what? Well, we can make them. We can measure them, at least three things. How do we see them? How do we know they're there? And the reason we can see them is something called an accretion disk. That's what lets us see black holes. An accretion disk is a swirling mass of hot gas surrounding the black hole. As it captures a star that comes close enough, the star will spiral in and leave behind an accretion disk. And the accretion disk is feeding stellar material, hot gas, into the black hole. The black hole is at the center. But there's more. As well as the accretion disk, that's in blue according to this artist's conception, there are two bipolar jets coming out from the top and the bottom, and they're jets of hot plasma, and they go out for long times. And they don't start at the black hole, they start at the edge of the black hole. They're not really produced by the black hole. In fact, we do not really know why jets occur. We know they're there because we can see them, but we don't know why they occur, because they don't start at the black hole, they start at the edge of the black hole. Okay? Now, an accretion disk feeds the black hole. It takes X-ray eyes to see the accretion disk. That's the hot gas. You need an X-ray eyeball. The jets, you see, you need a radio eyeball. And supermassive black holes make supersized jets. And I have a little video, I think is the next slide. No, it's not. What was the first black hole that was discovered? There was an X-ray image of SIGX-1. It's the X-ray source that was discovered in 1972, and the X-ray source orbits the big blue star every 5.6 days, and it has a mass of about 30 solar masses. So it was very curious. How can you have an X-ray source that's that massive orbiting a star? It must be a black hole, maybe. It was the subject, of course, of another bet. In 1974, the wager, if black holes didn't exist, Thorne had to cough up a 4-year subscription to the British magazine Private Eye. If black holes existed, Hawking had to cover a 1-year subscription of Penthouse for Kip Thorne. And Kip, after decades of work, people concluded that this was a real black hole, strong case, and Hawking did what he called the gentlemanly thing. He broke into Thorne's office, signed the original paper, and sent the winner, Kip Thorne, a year of Penthouse magazine. So here is SIGX-1 with different pieces. The black hole is 21 solar masses. On the left side is an optical image of SIGX-1, the blue star. The black hole is in the center of that little swirly thing, and the accretion disk is the swirly thing. That's what you see with X-ray eyes. And then the black hole is spinning 800 times a second. And down in the lower right is an X-ray image of SIGX-1. And the jets are coming out. That's a picture of actual radio image of a jet coming out from the center of that black hole. And here is a video describing what's going on with a supermassive black hole.
This is the giant elliptical galaxy Centaurus A. Radio and X-ray images reveal features associated with jets driven by the galaxy's supermassive black hole. Now, the Tanami project has provided the best ever view of these jets. In this radio image of the galaxy's core, the black hole is invisible, but the jets show in great detail. Features as small as 15 light days across can be resolved. The powerful jets feed vast loads of radio-emitting gas that reach far beyond the visible galaxy.
This is that was a NASA video, but Centaurus A is one of my favorites because the black hole this is an optical image of the galaxy with a radio image of the jets overlaid on it. The jets are in blue and red, the optical image is in white, and the 55 million solar mass black hole is in the center. The trick is that the jets are 1 million light years long, and Centaurus A is only 15 million light years away. So if these are 1 million light years long, they stretch over 1/15 of the distance from us to them. And the next image shows you what the jets would look like if you had radio eyes. And the image, the little bright dot, is actually the moon. It's an image of the moon used there for scale. And this is Centaurus A, and what it would look like in the sky, stretching over 1/4 of the sky, if you had radio eyes and were able to see it in radio. And I think that's very impressive, that it's just humongous. These jets are real, and they're enormous, and they're very powerful. Now, the Milky Way has a center. The Milky Way picture in the bottom is a picture of the Milky Way, and it's stretched out linearly. It's flat. It's pretty flat. Left to right, right to left. And we're on the upper left, we're going into the center of Sagittarius A star is the name of the center, and we're going in on from the constellation Sagittarius into the center of the Milky Way to a 4 million solar mass black hole. The closer we get, we have to change from optical light to infrared light, and we slowly get to a little rectangle that's right there at the center. And if you watch those stars move over a period of 10, 15 years, they actually orbit the black hole. That's not a simulation. Those are real stellar motions where they followed the star over time, several stars over time. In fact, the next image shows the star S2, which is the upper red circle, and it has a complete orbit. It's been around the black hole one complete time, and it's going to get eaten pretty soon. And then the star 102 is the white circle. And they have followed these stars with the Keck telescope from 1995 through 2012. And they actually mapped out their motions. That's just incredible, incredible feat. Now, black holes, as I said, with OJ 287, can come in pairs. And once they start circling each other, they merge. And this is the one with 2 billion solar masses, 3 gigalight years distant. That's OJ 287. And if we did a simulation of merging black holes, which is what they're going to do, they're not merged yet. The Finnish group has been watching them for 20 years, and they haven't merged yet, but they're going to merge. And if we can play the video, you see them circling around each other, and on the bottom is what it would look like in sound waves if you had a sound wave mapped to the motion of the black holes. But the two black holes are circling around each other, coming closer and closer. And as they get towards the end, the frequency actually increases, and they go faster and faster. We've actually measured this. We know that they go faster and faster. People have seen this. They go faster and faster, and right just as it gets to the end and they merge, you hear a which is the LIGO chirp, if you've heard of the LIGO chirp from the LIGO data. And the two black holes merge. And I think that's an exciting video to watch, because you not only see them merge, but you know about the LIGO chirp. And so now that we've done that, what do we know? We know a lot about the outside. We have a lot to learn about the inside. However, we do know they're out there. We can detect them indirectly, but we can detect them. And LIGO has detected them directly. And so if we can do that, we can still enjoy the beauty. And I choose this particular starry night because Van Gogh was in an audience with an astronomer giving a talk showing drawings of galaxies he had made. And he made a drawing of the galaxy M51, the Whirlpool galaxy. And Van Gogh put it in the center of his painting. That swirl right in the center is the galaxy M51, the Whirlpool galaxy. And I think that's an exciting combination of art and science come together. So thank you very much for listening, and I hope you've learned a little bit about black holes.
Well, thank you, Sethanne. During your talk, you did have a question.
Oh.
And Steve wants to know, how fast will you be going when you reach the event horizon? You were talking about going faster than the speed of light and slower than the speed of light. So how fast would you be going if you actually...
If you get to the edge, you've got to travel at the speed of light to get to the edge, which means you can see the back of your head. Actually, as you go around the edge, you actually see the back of your head because the speed of light is as fast as you can go. So if you're watching from a long distance away, you don't see that. But you yourself, as you fall in, you're traveling at the speed of light as you cross the event horizon.
So at that boundary, you would be traveling at the speed.
Mm-hmm.
So if you've got a couple of more minutes, we do have a couple of folks out there. If anybody has any additional questions, Sethanne Howard could answer this. Oh, we do have a question. So let's see here. What else can we expect to learn from LIGO and the Event Horizon Telescope?
Well, they have now, I think, 80 events. They have measured a neutron star merger, a neutron star black hole merger, and a black hole merger, and they've got over 80 of these. So we're going to learn about masses, the general theory of relativity, the early universe. LIGO is going to tell us a lot of information. And I think the LIGO does a dance. The LIGO is an interferometer, and it does a dance. It does this as the gravitational wave comes by LIGO, the two arms do a dance like this. And that's the LIGO dance. And at the end, as they merger, you hear the chirp at the end because they're going so fast that they make that the sound actually becomes loud enough to hear, and they can actually hear it at the LIGO station.
So it sounds like if they have over 80 events in just a few years, right, that they've been... Does this mean that these events are happening more frequently than we previously thought?
Maybe. We don't know, because previously what we thought, we don't know whether it's right or not. It just was a theory. It just was a hypothesis. So we don't know if they're happening more frequently. That's one thing LIGO will tell us, how frequently these things do occur throughout the universe.
Okay, we have another question. What is the largest group of black holes we've observed? You've mentioned binary. Are there groups of 3 or more black holes?
Not that we know of. There could be. I'm not saying there aren't, but we don't know of any yet.
Do we think that binary black holes are fairly common?
Yes, because any galaxy in a group, if there's a galaxy in a group, you're going to have binary black holes because the galaxies are slowly swirling, very slowly, but very slowly swirling around each other. And the black hole in the center of each one is going to swirl around. And as the galaxies merge, and galaxies, they call it cannibalism. The bigger galaxy eats the little galaxy, and the black holes will merge.
And by slowly, And by slowly, you're talking about hundreds of millions or billions of years, correct?
Yes, hundreds of millions of years. M51, it has a little tiny galaxy going around it that we know, that we can see, and it takes about 200 million years to go around once, orbiting. But it's close in. It's going to orbit faster and faster until it's finally cannibalized.
You have one more question here. Is the black hole in the center of our galaxy, the Milky Way, the result of a merger of other black holes?
Probably. Because the Milky Way has cannibalized a lot of little tiny galaxies around it. And I'm sure that they've all merged to make this supermassive black hole at Sagittarius A star. Yes.
Okay. Well, let's see. Are there any other questions in the chat?
Oh, those are good questions.
We do have one more here. How long will it take for Milky Way and Andromeda to merge? Once they start passing by each other, we're still pretty far away from each other, right?
Still pretty far away from each other, and it's going to take millions and millions and millions of years, and it may not. We may miss each other. Some simulations show that we're going to miss. Some simulations show that we're going to actually merge. So it depends on who you believe in their computer simulation of merging galaxies. And just a second, I'll turn this off. There.
Okay. Well, I'm not seeing any.
Turn it off. Let me.
Oh, actually, we do have another question.
Did I answer that one enough before my phone rang?
I think so. But we do have a question about what would happen if our sun became a black hole. Now, you addressed this a little bit in your talk, but could you reiterate that?
If the sun all of a sudden became a black hole, would we notice? And yes, we would, because we would die. Because there's no sunlight. And it's sunlight that gives us life. So the Earth, on the other hand, that we live on, our Earth won't care. It's going to continue to orbit the sun just as it did before. It's not going to swirl in. It's too far away. Remember, the Schwarzschild radius for the sun is 9 kilometers. So you have to be within 10, 11 kilometers of the edge of the sun to get swept in. And we are much further away than that on the Earth. So the Earth will just continue to circulate as before, so it won't care. But we will all die.
Well, that's cheery.
That's
but not a likely event, right? The sun is too small to really become a black hole.
The sun is too small to become a black hole. Exactly right. It's a wimpy star as stars go. Our sun is kind of wimpy.
Well, I'm sure it doesn't want to think so.
No, it doesn't want to think so. But it's got 5 billion more years before it evolves into a white dwarf.
Okay. Well, if anybody has any further questions, or would like to talk to you about this, they can get hold of you via email, correct?
Yes.
All right.
That's my email address. And don't forget the H at the end. It's my first name followed by an H at msn.com. It turned out when I asked for that name, somebody already took the name Sethanne, which surprised me. So I Googled it and found out there's another Sethanne in Iowa.
Excellent.
I'm going
to do one more check to see if there's any other questions in the chat. And thank you so much for this very enlightening talk. I've certainly learned a lot about black holes, which I find fascinating. And I don't see anything else in the chat, so I just want to remind everybody that you can find our website at friendsoftheplanetarium.org, and that we are always looking for more members. You can join or donate via the website. And while we are temporarily closed, again, I mentioned this at the beginning, we are still here, and we're working towards making sure that the planetarium is updated and improved when it reopens, hopefully in 2022. And we hope to see you there. But in the meantime, keep looking. We will have more virtual events, and hopefully as the year moves on in 2022, we will have some in-person events. I want to thank you again, Dr. Howard.
It's a wonderful planetarium. I've been there several times. It's a wonderful planetarium.
We love it, and we hope there will be some new and interesting shows when we reopen. We hope that you'll all come visit us. And until then, thanks so much, and keep watching the skies, and we'll see you soon.